So just as in the Laplacian smoothing example before, the value of k is a smoothing parameter. It makes the function less scattered. Here's an example of k equals 1. For a two-class nearest neighbor problem, you can see the separation boundary is what's called the Voronoi diagram between the positive and negative class, and in cases where there's noise between these class boundaries, you'll find really funny complex boundaries as indicated over here. Particularly interesting is this guy over here, where the class of this circle over here protrudes way into the otherwise solid class. Now as you go to k equals 3, you get this graph over here, which is smoother. So if you're over here, your two nearest neighbors are of this type over there, and you get a uniform class over here. In this region over here, you get uniform classes as solid classes, as shown over here. The more you drive up k, the more clean this decision boundary becomes, but the more outliers are actually misclassified as well. So if I go back to my k nearest neighbor method, we just learned that k is a regularizer that controls the complexity of the k nearest neighbor algorithm, and the larger k is, the smoother the output. We can once again use cross-validation to find the optimal k, because there's an inherent trade-off between the complexity of what we want to fit and the goodness of the fit. What are the problems of kNN? Well, I'd argue there's two. One is very large data sets, and one is very large feature spaces. Now the first one results in lengthy searches when you try to find the k nearest neighbors. Now fortunately, there's methods to search efficiently. Often you represent your data not by a linear list, in which case search would be linear in the number of data points, but by a tree where the search becomes logarithmic. The method of choice is called KDD trees, but there's many other ways to represent data points as trees. Now, very large feature spaces cause more of a problem. It turns out computing nearest neighbors as the feature space for the input vector increases becomes increasingly difficult, and the tree methods become increasingly brittle. And the reason is shown in the following graph. If you graph your input dimension to the average edge length of your neighborhood, you'll find that for randomly chosen points, very quickly, all points are really far away. The edge length of 1 is attained if your query point is unit 1 away from the nearest neighbor. If you have 100 dimension, that is almost certain. Why is that? Well, in 100 dimension, there ought to be one where just by chance you're far away. The number of points you need to get something close grows exponential with the number of dimensions. So for any fixed data set size, you will find yourself in a situation where all your neighbors are far away. Nearest neighbor works really well for small input spaces like 3 or 4 dimensions. It works very poorly if your input space is 20, 25, or maybe 100 dimensions. So don't trust nearest neighbor to do a good job if your input dimension space is high. So congratulations, you just learned a lot about machine learning. We focus on supervised machine learning, which deals with situations where you have input vectors and given output labels, and your goal is to predict the output label from an input vector. And we looked into parametric models like naive Bayes, non-parametric models. We talked about classification, where the output is discrete, versus regression, where the output is continuous. And we looked at samples of techniques for each of these situations. Now obviously, we just scratched the surface on machine learning. There's books written about it and courses taught about it. Machine learning is a super fascinating topic. It's the one that within artificial intelligence I love the most. It's really great about the real world as we gain more data, like the World Wide Web or medical data sets or financial data sets. Machine learning is poised to become more and more important. I hope that the things you learned in this class so far really excite you and entice you to apply machine learning to problems that you face in your professional life.